Welcome to Deep Space Intelligence. My name is Liam, and if you are new here, this channel is dedicated to exploring the most extraordinary discoveries at the frontier of modern astronomy and astrophysics. We dig into the science, we sit with the uncertainty, and we follow the evidence wherever it leads, even when it leads somewhere that makes your mind stretch in directions it was never designed to stretch. And today, the evidence leads to one of the most astonishing moments in the history of observational astronomy. Somewhere in the direction of the constellation Virgo, roughly 300 million light-years from where you're sitting right now, something just happened that the universe had been keeping secret for an unimaginably long time. A sleeping giant has opened its eyes. A black hole that had been completely, utterly silent for as long as complex life has existed on Earth, and longer, perhaps longer than our entire solar system has existed in its current form, has roared back to life. And the most remarkable part of this story is not just that it happened. The most remarkable part is that we were watching. In the entire history of modern astronomy, we have never caught a supermassive black hole in the precise act of waking up. We have found active black holes that were already blazing when we first pointed our telescopes at them. We have found dormant black holes sitting quietly in the cores of otherwise unremarkable galaxies, invisible to our instruments, hinting at themselves only through the gravitational effects they impose on the stars and gas surrounding them. But to capture the actual moment of transition, to have a galaxy in our databases that we know was ordinary and quiet, and then to watch it transform, watch it begin to flicker and then erupt across a distance of 300 million light-years in real time as measured by human observers, that is something genuinely new. That is something that has never been done before. And today we are going to walk through exactly what scientists found, exactly how they found it, and exactly why the global astrophysics community is paying such intense and focused attention to what this awakened giant does next. Before we dive in, I want to say something that is important to me as the person who puts these documentaries together. Everything we discuss here is grounded in peer-reviewed research, in published scientific findings, and in statements from researchers at institutions including the European Space Agency, NASA, the European Southern Observatory, Valparaiso University in Chile, Midnapore City College in India, the Massachusetts Institute of Technology, and universities and research institutes spanning multiple continents. The findings we cover today were published in prestigious journals including Nature Astronomy, Astronomy and Astrophysics, and the monthly notices of the Royal Astronomical Society. But space science is a living, breathing, evolving discipline, and our understanding changes as new data arrives, as new instruments come online, and as theorists devise better ways to model what we're seeing. I always encourage you to read the original papers, cross-check the sources we list in our descriptions, and form your own considered views about what the evidence means. Great science begins with curiosity and independent thinking, and that applies every bit as much to you watching this as it does to the astronomers and physicists doing the work. Now, let us talk about black holes, and why the silence of one is almost as profound as the sound. To truly appreciate why the awakening of a dormant black hole is such an extraordinary event, you first need to understand what a supermassive black hole actually is when it is sleeping. When most people imagine one of these objects, they picture something perpetually violent, a churning vortex of doom and destruction at the center of a galaxy, constantly devouring everything around it, spitting out relativistic jets of superheated plasma, lighting up the universe in every wavelength of the electromagnetic spectrum. This image is not invented from nothing. Some black holes really do look something like that. The central engines of quasars, the most luminous objects in the known universe, are supermassive black holes consuming material at extraordinary rates, converting the gravitational potential energy of infalling mass into radiation with an efficiency that no nuclear reaction, no fusion bomb, no stellar core could approach. A sufficiently fed black hole can outshine its entire host galaxy by a factor of hundreds or even thousands. It can be visible across literally billions of light-years of space. But that image is deeply misleading in an important way, because it suggests that this behavior is the norm, the default state of a supermassive black hole. The truth, revealed by decades of careful survey work and statistical analysis, is almost the opposite. Most supermassive black holes, the vast majority of them in the nearby universe, spend most of their time in a state that is astonishingly, almost eerily quiet. They sit at the centers of their galaxies doing very little. They are not consuming large quantities of matter. They are not generating relativistic jets. They are not producing significant radiation in any wavelength we can easily detect. They are simply there. Enormous concentrations of mass-distorting spacetime in their neighborhoods, influencing the orbits of nearby stars and the distribution of surrounding gas, but essentially invisible to our instruments in any directly energetic sense. Our own Milky Way's central black hole is a perfect and instructive example of this. Known as Sagittarius A star, it weighs approximately 4 million solar masses, making it a genuine giant by most measures. But by the standards of the active galactic nuclei we observe in distant galaxies, Sagittarius A star is almost laughably quiet. It occasionally produces small flares of radiation, typically when a tiny clump of gas or some other wisp of material approaches, closely enough for a small amount to fall toward the event horizon. The black hole produces modest bursts of infrared and X-ray emission on timescales of hours, events that the innermost stars of our galaxy can be caught reacting to, their orbital velocities perturbed by the same gravitational influence that produces the flares. But these are whispers. On the cosmic scale of what active black holes can do, Sagittarius A star is essentially dormant, a giant sleeping in the dark at the center of the galaxy. The same is broadly true of the supermassive black hole in Andromeda, our nearest large galactic neighbor at about 2.5 million light-years. And the same is true of the central black holes of the vast majority of ordinary spiral and elliptical galaxies in our cosmic neighborhood, vast in mass, profound in gravitational influence, but quiet. This is not the exception. This is the rule. Astronomers have known for some time that supermassive black holes spend long periods inactive. The reasons come down to a simple and somewhat counterintuitive principle. A black hole can only consume what is delivered to it in the right way. If there is no material flowing toward the center of a galaxy in sufficient quantities, and at the right angular momentum to form and sustain an accretion disk, the black hole simply sits there, empty and waiting. A gravitational well without anything to fall into it. The extreme efficiency with which a properly fed black hole converts mass into energy also means that even a modest accretion rate can produce a very bright active nucleus. But if the accretion rate drops to essentially zero, the brightness drops accordingly, down through the noise floor of our instruments, down to nothing detectable. What triggers the feeding to begin? What fills an accretion disk that had previously been empty? The mechanisms are varied and not yet fully understood, which is itself a significant open problem in astrophysics. Galaxy mergers are one major driver. When two galaxies collide and merge, the tidal forces and gravitational torques generated by the interaction can funnel enormous quantities of gas toward the nucleus of the merged system, delivering fresh fuel to the central black hole on a timescale of hundreds of millions of years. Tidal disruption events, where a star that passes too close to the black hole gets torn apart by tidal forces, can trigger a brief but intense episode of accretion as the stellar debris rains down on the galactic center. Large-scale instabilities in the disk of gas in a galaxy can gradually channel material inward over millions of years through a process called secular evolution. And then there are more subtle mechanisms, including the cooling of hot gas in the surrounding environment that deposits cold gas near the nucleus, or stellar feedback from a burst of star formation that restructures the gas distribution and redirects material toward the center. The critical point is this. The transition from dormant to active is not an instantaneous flip of a switch. It is a gradual process that can unfold over years, decades, centuries, or even longer timescales before the black hole crosses the threshold from invisible to unmistakably bright. And it is precisely this transition, this actual awakening moment observed in real time as it happens, that astronomers had never directly caught before the events we're about to describe. Because there is a fundamental observational challenge. If a black hole is dormant, it produces essentially no detectable radiation. Your telescope sees nothing noteworthy. And if a black hole is already active and has been for a long time, you see a bright nucleus when you look at it. But you have no way of knowing from that snapshot alone when the activity began, or how the system looked before it started. You are seeing a frame from the middle of a movie with no knowledge of the earlier frames. You cannot look at a blazing active galactic nucleus and say with confidence that 3 months ago it was quiet, because you simply were not watching 3 months ago, and you have no baseline to compare it against. What astronomers needed, what they had essentially been hoping for without knowing when it would happen, was a galaxy they had watched being quiet for long enough to establish a solid baseline, a galaxy sitting in the databases of systematic sky surveys, catalogued as ordinary and inactive over years of repeated observations, so that when something changed, they would know with certainty that they were watching a real-time transformation from quiet to active. That is exactly what the universe delivered. The galaxy is catalogued in the Sloan Digital Sky Survey under the designation SDSSJ 133519.91 plus 0728, 07.4, which for obvious practical reasons astronomers have shortened to SDSS 1335 plus 0728. It sits approximately 300 million light-years from Earth in the direction of the constellation Virgo, and before late 2019, it was by every measurable standard completely and unremarkably ordinary. The Zwicky Transient Facility, a powerful survey telescope at Palomar Observatory in California that systematically monitors the sky in optical wavelengths, looking for changes in the brightness of hundreds of millions of celestial objects, had watched this galaxy for years. Its automated alert stream, which flags statistical deviations from expected brightness, had never generated a significant alert for SDSS 1335 plus 0728. No variability, no brightening, no sign of any nuclear activity whatsoever, just a quiet galaxy, 300 million light-years away, going about whatever it is that quiet galaxies do. Then, in December of 2019, something changed. The Zwicky Transient Facility's automated pipeline flagged an anomaly. The nucleus of SDSS 1335 plus 0728 had brightened significantly. Not by a marginal amount within the normal scatter of background variability, but by a clear and substantial margin. The source was formally designated ZTF19ACNSKYY in the Zwicky system, later updated to ZTF22ABYH-AUT. Across observations in multiple wavelength bands, the core of the galaxy was unambiguously brighter than it had been for the entire prior observational history that astronomers could access. By May of 2020, the nucleus had reached its peak brightness, brightening by roughly 20% in the optical, compared to its prior baseline according to researchers involved in the analysis, and it had been exhibiting ongoing stochastic variability ever since, with its luminosity remaining elevated above the previous level for more than 1,680 days, as of early 2025 when the key findings were being written up. The team that first noticed and investigated this event was led by Paula Sanchez-Saez, a researcher at the European Southern Observatory in Germany. When they identified the optical brightening, they did what any diligent team of astronomers would do. They triggered follow-up observations using NASA's Swift X-ray Space Telescope to look for high-energy radiation, and they also went through archival data from the Erosita All-Sky X-ray survey to see whether any X-ray emission had been recorded. They found nothing, no X-rays. Whatever was causing the optical brightening was not yet producing detectable high-energy radiation, at least not at the sensitivity levels accessible at that time. The galaxy was brightening in visible light, but the X-ray universe seemed unaware of it. The team spent the following years carefully analysing the data from this galaxy, building up as complete a picture as possible of what was happening, and comparing it against known categories of transient phenomena. A tidal disruption event, where a black hole tears apart a passing star, produces a characteristic light curve with a specific rise and fall profile that plays out over weeks to months following a recognisable decay law. Supernovae produce sharp, distinct brightness peaks that fade in ways that depend on the physics of the explosion and the type of supplosion. Active galactic nuclei have their own spectral fingerprints and characteristic variability patterns that distinguish them from other classes of transient events. What the team saw in SDSS 1335 plus 0728 fit none of these categories precisely, or rather, it fit one category better than any of the alternatives: a newly activating active galactic nucleus. The persistent brightening, lasting years rather than weeks or months, and showing no sign of fading back to the baseline. The stochastic variability pattern, flickering and fluctuating in a way consistent with ongoing accretion. The spectral changes in the nuclear emission, showing the characteristic signatures of ionized gas illuminated by a central engine. All of it pointed toward one conclusion: the supermassive black hole at the center of this galaxy was switching on. It was entering an active phase, and given the years of pre-existing observational data showing nothing unusual, the team could say with confidence that this activation was recent, happening on a human observable timescale. The bright, compact central region was reclassified as an active galactic nucleus candidate. Researchers gave it an informal nickname drawn from the original Zwicky Transient Facility source designation, where the event was first catalogued. They called it Ansky, a name borrowed from the Sky Survey data, but now attached to one of the most scientifically valuable black holes in the observable universe. But Ansky had not yet fully revealed what it was capable of. For more than 4 years after the initial optical brightening in December 2019, Ansky sat in a kind of liminal state. It was clearly brighter than it had been. Its nucleus flickered and varied in ways that were consistent with ongoing accretion activity. But it had not yet done anything that would mark it as particularly dramatic by the wider standards of black hole astrophysics. It was like a dormant volcano showing signs of geological unrest, elevated surface temperatures, increased gas emissions, measurable seismic activity, but not yet erupting in any visually spectacular way. The seismographs are twitching. Something is building, but the eruption has not come yet. Then, in February of 2024, Ansky erupted. The team that caught this new development was led by Lorena Hernández-García, a researcher at Valparaiso University in Chile, also affiliated with the Millennium Institute of Astrophysics and the Millennium Nucleus Titans. Her team had been monitoring Ansky as part of a broader observational program tracking the galaxy's evolution, following the initial optical activation, and in February 2024 they detected something completely unexpected when they looked at the X-ray data coming from the nucleus. They saw bursts, powerful, regular, repeating bursts of X-ray radiation erupting from the galactic center with a rhythm that was startlingly precise and an energy that was extraordinary. These were not random flares. They were not the kind of stochastic flickering that had characterized the optical variability since 2019. These were periodic, organized. They recurred on a timescale of approximately 4.5 days, making them the longest period events of their class ever recorded by astronomers up to that point. Each individual burst lasted for roughly a day and a half, meaning that Ansky was spending a substantial fraction of each 4.5-day cycle in a state of intense and measurable X-ray emission. And the energy released in each of these eruptions was not just significant, it was extreme. The phenomenon these bursts represent has a formal name in astrophysics, quasi-periodic eruptions, or QPEs. The term was coined only in 2019 when the first examples were discovered, making this an entirely new class of astrophysical phenomenon that did not even have a name until very recently. QPEs are rapid, recurring X-ray bursts from the vicinity of supermassive black holes, and at the time Ansky was discovered to be producing them, only a handful of examples had been found across the entire observable universe. The phenomenon remains, by the honest admission of researchers working on it, deeply mysterious in its origin. The leading hypothesis is that QPEs arise from some kind of repeated interaction between an accretion disk surrounding the black hole and another object orbiting within or near that disk. Perhaps a stellar mass black hole, a neutron star, or some other compact remnant that has been captured into an orbit spiraling gradually inward. Each time this orbiting object plunges through the plane of the accretion disk, it generates a violent shock, a collision with the dense, superheated, rapidly rotating material of the disk, and that collision releases a burst of X-rays. But Ansky's QPEs are not simply members of a known class. They are so extreme in their observable properties that they challenge and strain the theoretical models that astronomers have constructed to explain the phenomenon based on the earlier known examples. The comparison in numbers is stark and worth sitting with for a moment. Typical QPEs from other known sources last for perhaps an hour or two before fading. Ansky's eruptions last approximately a day and a half, 10 times longer. Typical QPEs recur every few hours. Ansky's recur every 4 to 5 days, making the recurrence timescale also roughly 10 times longer than typical. At the peak of each burst, Ansky is roughly 10 times more luminous in X-rays than a typical QPE source at its peak. And when researchers integrated the total energy released across the full duration of each burst, rather than just the peak luminosity, the numbers became even more dramatic. Each individual eruption from Ansky releases approximately 100 times the energy of a typical QPE burst from other known sources. By April of 2025, when the key findings were published in the journal Nature Astronomy in a paper titled Discovery of Extreme Quasi-Periodic Eruptions in a Newly Accreting Massive Black Hole, researchers had documented 165 separate eruptions from Ansky. 165 individual X-ray outbursts, each releasing 100 times the energy of a normal QPE, collectively adding up to an energy budget that speaks to the extraordinary physical processes at work in the nucleus of that distant galaxy. The paper itself was a genuinely large collaborative effort spanning dozens of institutions across multiple continents. The observational data was contributed by a fleet of some of the most powerful X-ray telescopes ever constructed and placed in orbit. ESA's XMM-Newton spacecraft, operated by the European Space Agency and positioned in a highly elliptical orbit that allows it to observe for long uninterrupted periods, is particularly well suited to this kind of study because it is the only telescope sensitive enough to detect the faint but important background X-ray emission from Ansky during the quiet intervals between eruption peaks. This background emission, which reflects the ongoing but less dramatic accretion activity between the main bursts, is scientifically crucial because it allows researchers to characterize the baseline state and compare it directly against the eruption state, quantifying precisely how much brighter and more energetic the eruptions are relative to the underlying activity. NASA's NISA instrument, the Neutron Star Interior Composition Explorer, installed aboard the International Space Station, contributed its extraordinary timing precision to the observations. NISA is specifically designed for high-cadence, high-time resolution observations of X-ray sources, and its ability to measure the precise arrival times of individual X-ray photons makes it ideally suited for studying periodic phenomena where the timing information itself encodes critical details about the orbital dynamics of the system. By tracking precisely when each eruption begins, reaches its peak, and decays back to the baseline, NISA data allows researchers to measure the evolution of the burst recurrence period with high accuracy, which in turn constrains the rate at which the orbital configuration of the erupting system is changing over time. NASA's Chandra X-ray Observatory, launched in 1999 and still operating 2.5 decades later, well beyond its original design lifetime through a combination of excellent engineering and careful orbital management, brought its unmatched spatial resolution to bear on the problem. Chandra's ability to produce sharp X-ray images and pinpoint sources to within fractions of an arc-second on the sky confirmed beyond doubt that the eruptions were originating from the precise nuclear location of the galaxy, not from some other source nearby that might have been creating a confusing signal. This positional confirmation is essential in high-energy astrophysics, where the detectors that collect the most photons often sacrifice spatial resolution to do so. NASA's Neil Gehrels Swift Observatory contributed the long baseline of monitoring that documented the entire history of Ansky's evolution, from the initial optical brightening in late 2019 through the onset of X-ray eruptions in early 2024, and the subsequent ongoing activity. Swift's quick response capability and its ability to observe in both optical and X-ray wavelengths simultaneously make it invaluable for catching and characterizing new transient events in their early stages. Together, these four instruments provided a multi-layered, multi-year observational portrait of an awakening black hole that is simply unprecedented in the scientific literature. No single observation would have been convincing alone, but the combination of XMM-Newton detecting the eruptions and characterizing the energy spectrum, NISA precisely measuring the timing and periodicity, Chandra confirming the nuclear origin, and Swift providing the historical context across years of monitoring creates a body of evidence that the scientific community has received as genuinely compelling and novel. Now I want to try to give you a sense of the physical scale and nature of what is happening at the center of that galaxy 300 million light-years away, because the numbers alone, impressive as they are, do not fully convey the reality of the situation. Imagine a region of space that, while vast by any earthly standard, is actually compact by cosmic standards, a volume roughly comparable in size to our solar system out to Neptune. Within that region sits an object with a mass of approximately 1 million times that of our Sun. This is Ansky's central black hole, a relatively modest specimen by supermassive standards, lighter than the Milky Way's Sagittarius A star by roughly a factor of 4, but still a concentration of mass so extreme that the mathematics describing its neighborhood break with our intuitions entirely. Within a certain radius, the Schwarzschild radius, which for this particular black hole works out to a few million kilometers, space-time is so severely warped that all possible futures lead inward. That is the event horizon. That is the point of no return. Surrounding this object is an accretion disk, a broad, flat, rapidly rotating structure of superheated gas and plasma that has been assembling itself from material gradually delivered to the galactic center over years and decades, drawn inward by the immense gravitational pull of the central mass. This disk is not cool. The inner regions of accretion disks around supermassive black holes reach temperatures of millions to tens of millions of degrees, hot enough to emit copiously in X-ray wavelengths. The viscous friction within the disk, driven by magnetohydrodynamic turbulence generated by the magnetorotational instability, gradually transports angular momentum outward and allows material to spiral inward, falling ultimately through the innermost stable circular orbit and then plunging toward the event horizon, releasing its gravitational potential energy as radiation. And then there is the third player in the Ansky system. Orbiting somewhere within or near this disk, according to the most favoured current theoretical interpretation, is a much smaller but still substantial object. Perhaps a stellar mass black hole of somewhere between 10 and a few tens of solar masses. Perhaps a neutron star or a white dwarf. A compact remnant that has been captured into an orbit around the central million solar mass black hole, an orbit that is decaying over time as gravitational wave emission carries away the orbital energy and brings the smaller object gradually closer to the larger one. This system is what astrophysicists call an extreme mass ratio in spiral, or EMRI. The two masses involved are so wildly different, with the larger perhaps 100,000 times the mass of the smaller, that the interaction between them is highly asymmetric. The smaller object orbits the larger without significantly perturbing it. The dynamics of the smaller object's orbit are dominated by the gravitational field of the central black hole, and that orbit evolves slowly under the influence of energy loss to gravitational wave emission. Over thousands to millions of years, the smaller object spirals inexorably inward, making ever tighter orbits until it eventually crosses the event horizon and is swallowed. But before that final plunge, during the inspiral phase when the orbit still crosses the plane of the accretion disk on each revolution, something spectacular happens. Each time the orbiting compact object plunges through the disk, it collides with the accreting material at a relative velocity that can be a significant fraction of the speed of light. The resulting shock is violent and brief, a sudden violent compression of disk material, a spike in temperature to tens of millions or hundreds of millions of degrees, a burst of high-energy radiation propagating outward from the collision site. This is, in the current leading theoretical framework, what we observe from Earth as a quasi-periodic eruption. The 4.5-day recurrence period of Ansky's QPAs corresponds, in this picture, to the orbital period of the compact object around the central black hole. At the distance from the central black hole implied by this orbital period, which can be calculated using Kepler's laws in their relativistic form, the orbiting object is moving at an enormous velocity, sweeping through its orbit in just 4.5 days. As the orbit slowly shrinks under the influence of gravitational wave emission, that orbital period will gradually decrease over years and decades, and we would expect to observe the QPE recurrence time shortening accordingly. This provides a direct observational prediction that can be tested by continued monitoring of the system, one of several ways in which the theoretical models make specific, falsifiable claims about what we should observe if the EMRI disk collision picture is correct. However, I want to be careful here, because the theoretical picture is not as clean and settled as that summary might suggest. There are genuine complications. The EMRI disk collision model for QPEs is the leading hypothesis, but it is not the only one, and Ansky's particular properties create specific difficulties for even the leading model. One major puzzle is the context of the activation. The standard scenario for QPEs in other known systems involves a tidal disruption event, the shredding of a passing star, as the mechanism that creates the accretion disk with which the orbiting compact object then collides. In those systems, the QPEs appear relatively soon after the tidal disruption event, and the disk they occur in is the debris disk left by the disrupted star. But in Ansky's case, the situation is different and arguably more complex. The optical brightening that began in 2019 has some characteristics that overlap with tidal disruption events, but after years of monitoring, it has settled into a pattern that looks much more like a newly activating active galactic nucleus, a turning on AGN, than a post-tidal disruption decay. The persistent brightening, the ongoing stochastic variability, the spectral characteristics all point more toward a newly formed accretion disk being fed by some mechanism other than a single recent stellar disruption. This is what makes Ansky scientifically novel and theoretically exciting in a way that goes beyond its intrinsic drama. If QPS can occur in the context of a newly activated AGN, not just in the context of a tidal disruption event, then the conditions for producing them are broader than previously thought. Any newly assembled accretion disk might be capable of generating this kind of interaction with a compact orbiting object. And that opens the question of how many other black holes in their early active phases might be producing QPEs that we simply have not yet detected, either because we have not been watching the right galaxy at the right time with the right instruments, or because the eruptions are happening at energies or timescales or distances that put them outside our current detection capabilities. The researchers in the Nature Astronomy paper proposed that newly activating AGN might actually be ideal environments for producing QPEs for a specific dynamical reason. When a supermassive black hole has been dormant for a long time, the region of space near the galactic center, the so-called loss cone of stellar orbits that lead toward the black hole, becomes gradually filled with stars whose orbital dynamics have not been strongly perturbed by accretion activity. When the black hole then activates and begins accreting, it encounters this rich population of stars at a variety of orbital energies and angular momenta. A fraction of these stars will be on orbits that eventually lead them close enough to the black hole to be captured into bound orbits, and some of those captured objects will have the right properties to produce long-lived EMRs that generate QPEs. Newborn AGN, in this picture, may produce QPS more readily than more established active nuclei precisely because they have a fresh, undepleted reservoir of nearby stars to draw upon. And Ansky was not yet done evolving. Through 2025, as the cadence of observations continued and the body of data from NISA, XMM-Newton and other facilities continued to grow, researchers began to notice that Ansky's behavior was changing in systematic ways. A follow-up study published in Astronomy and Astrophysics in November 2025, based on NASA observations conducted between January and June of that year, revealed that the QPEs were still occurring, but with properties significantly different from what had been documented in 2024. The 2025 eruptions were found to be approximately 4 times more energetic than those observed in 2024. The recurrence time between bursts had roughly doubled, from approximately 4.5 days to approximately 10 days. The individual burst durations had also grown, ranging from 2.5 to 4 days, compared to the roughly day-and-a-half duration seen in 2024. And perhaps most intriguingly from a theoretical perspective, the shape of the individual burst had changed in a specific and informative way. In 2024, the eruption profiles were relatively symmetric. The brightness rose toward the peak and then declined in a roughly comparable fashion. By 2025, the profiles had become distinctly asymmetric, with longer and more gradual decays after the peak compared to the rise. This asymmetry is not cosmetic. It carries information about the physical conditions at the collision site, about how the shocked plasma cools and expands after the initial impact, about how the disk material redistributes itself in the wake of each eruption. This evolving behavior is scientifically invaluable because a static system tells you relatively little compared to a dynamic one. If the QPEs always looked the same, you would have one set of observational constraints to match against your theoretical models. But when the system is visibly changing from year to year, when specific measurable properties are evolving in specific directions on specific timescales, each of those trends becomes an additional constraint. Different physical models make different predictions about how the burst properties should evolve as the system ages. The EMRI disk collision model predicts that as the orbit decays under gravitational wave emission, the recurrence time should decrease as the orbital period shortens. But the 2025 data showed the recurrence time increasing, not decreasing, which means either the simple EMRI picture needs to be modified or additional physical processes are at work. Some researchers have proposed that the lengthening recurrence times might reflect changes in the accretion disk itself rather than changes in the orbital period of the compact object. If the disk is still growing and its outer radius is expanding as more material is delivered to the galactic center, the geometry of the disk-orbiter interaction will change accordingly. The orbiter might be intersecting the disk at progressively larger radii as the disk expands, and larger radius intersections in lower density disk material would be expected to produce longer, more gradual eruption profiles with longer cooling times, which is consistent with the observed asymmetry. But this remains a hypothesis, one that is consistent with some of the data but not yet definitively confirmed. Erwin Quintin, an ESA research fellow and X-ray astronomer involved in the study, put the current state of affairs into honest perspective when he said that for QPEs, we are still at the point where we have more models than data, and we need more observations to understand what is happening. This is the genuine frontier of the science, a phenomenon that is clearly real, clearly extraordinary, producing data that is genuinely new and unprecedented, but whose full physical interpretation is still being worked out by some of the brightest minds in high-energy astrophysics. That is not a reason for frustration or disappointment. That is the definition of a scientific frontier. There is something I always find important to reflect on when discussing discoveries like this, and I want to share it with you as we move deeper into the story. As a channel, we work hard to present these findings accurately and with appropriate scientific nuance. But science is a process, and the most exciting moments in that process are often precisely the moments of deep uncertainty, when new observations have revealed something genuinely unexpected that does not yet fit neatly into existing frameworks. The honest answer to many of the questions Ansky raises is that we do not yet know, and the most honest thing I can say to you is that the researchers themselves, the people who built the instruments and analysed the data and wrote the papers, are still working it out. Wherever you encounter confident, simple, definitive answers about phenomena as complex as these, I would encourage you to probe a little deeper and see whether that confidence is actually earned. The universe rarely offers simple answers to profound questions. Now, while Ansky represents perhaps the most detailed and carefully observed case of a black hole awakening in recent history, it is not the only dramatic story of a dormant black hole returning to life, and the other major story emerging from this same period of research is, if anything, even more spectacular in its sheer physical scale and its implications for how black holes shape the universe around them. In January of 2026, a paper was published in the monthly notices of the Royal Astronomical Society by a team of researchers led by Shobha Kumari of Midnapore City College in India. The paper described observations of a galaxy known by its catalogue designation J, 1007+3540, obtained using two of the most sensitive radio interferometer arrays on the planet, the low-frequency array, known as LOFAR, which is a vast network of radio antennas spread across the Netherlands and neighbouring European countries, and the upgraded Giant Meter Wave Radio Telescope, or UGMRT, located in Pune, India. What those observations revealed was a portrait of black hole activity so visceral and so dramatically large in scale that the researchers themselves, publishing in the disciplined and restrained language of an academic journal, reached for the language of natural disaster to describe it. They called it a cosmic volcano erupting after ages of calm. The supermassive black hole at the heart of J 1007+3540 had been dormant for approximately 100 million years. 100 million years of complete silence, no jets, no significant radio emission. No detectable outpouring of energy from the galactic center in the radio wavelengths that trace the relativistic plasma ejected by active black holes. The machine had been switched off for 100 million years, and in its absence, the plasma structures from the previous active phase, the vast lobes of magnetized material that the black hole had injected into the surrounding space during its last episode of activity, had been slowly fading, their relativistic electrons losing energy to synchrotron radiation and inverse Compton scattering, their radio signatures growing dim and diffuse over the tens and hundreds of millions of years of quiescence. 100 million years ago, our planet was in the middle of the Cretaceous period. Tyrannosaurus rex had not yet evolved. The flowering plants that now cover the vast majority of Earth's land surface were in the earlier stages of their diversification. The continents were positioned somewhat differently than they are today, with a broad, warm, shallow sea cutting across what would one day become North America, and a land bridge connecting Africa to what would become Eurasia in the north. An outside observer looking at Earth from space would have recognized the general shapes of the continents, but would have found the biological and physical details of the planet deeply unfamiliar. During all of that vast stretch of cosmic time, the central black hole of J1007+3540 sat quiet. And then something happened. Something delivered material to the galactic center. Perhaps a collision with another galaxy. Perhaps the slow infall of cooling gas from the hot medium surrounding the galaxy. Perhaps a large-scale dynamical instability in the galaxy's own structure that channeled gas toward the nucleus. Whatever the trigger, the effect was unmistakable. The accretion disk reformed around the central black hole. The magnetic field built up to sufficient strength. The jets ignited. And when those jets ignited, they did not emerge into empty space. They emerged into an environment that had been shaped by the previous eruption 100 million years earlier. An environment filled with the fading plasma of the old lobes, with the hot gas of the surrounding galaxy cluster sculpted by tens of millions of years of interaction with that old plasma. The new jets, fresh and energetic, carrying newly accelerated particles at close to the speed of light, had to fight their way through this environment, pushing against the dense, hot, high-pressure intergalactic medium, encountering the resistance of a galaxy cluster that had been shaped by the very black hole now trying to push through it again. The radio images captured by LOFAR and UGMRT are genuinely extraordinary when you understand what you're looking at. LOFAR operates at low radio frequencies, roughly in the range of 100 to 200 MHz, wavelengths that are sensitive to relatively older, lower energy particles that have been radiating for a long time. This makes LOFAR ideal for tracing the extended ancient plasma structures from previous eruptions, the faded but still detectable remnants of earlier activity that would be invisible to higher frequency instruments. The UGMRT, operating at higher frequencies, is more sensitive to fresher, more energetic emission, and can pick out the compact, bright inner jet structures that mark the location of current activity. Together, the two instruments revealed a layered, stratified picture of J1007 plus 354. Oh, that reads like a geological cross-section through time. At the outermost edges of the image, extending to the north and south of the galaxy, are the faint, diffuse, ghostly remnants of the previous eruption. These ancient plasma lobes, estimated to be approximately 240 million years old, based on the energy loss rates of the synchrotron radiating electrons within them, represent what the black hole was doing before it fell silent. They are vast, spreading across enormous distances but faint, their constituent particles having lost most of their energy to radiation over the intervening 240 million years of cosmic time. Nested inside these ancient structures, in the inner regions of the radio source, are the brighter, more compact jet structures from the current eruption. These inner jets are estimated to be approximately 140 million years old, which means they ignited roughly 100 million years after the outer lobes were first produced. This is the dormancy period, written directly into the structure of the radio galaxy and the gap between two generations of plasma. You can quite literally read the black hole's history from the radio images. Here is when it was last active 240 million years ago, here is the silence of 100 million years, and here is the new eruption that is currently propagating outward through the cluster medium. The combined structure of J1007 plus 3540, the old lobes plus the new jets, stretches across nearly 1 million light-years of space. To put that number in human terms, the Milky Way galaxy, the vast spiral system that contains our solar system and roughly 200 billion other stars, is approximately 100,000 light-years in diameter. The radio structure of J1007 plus 3540 is 10 times wider than the entire Milky Way. The jets from this single reawakened black hole are carving through a volume of space so enormous that our entire galaxy would fit inside it 10 times over. What is making the new jets look so dramatic, so obviously distorted and compressed in the radio images, is the environment through which they are propagating. J1007 plus 3540 lives inside a massive galaxy cluster, one of the largest gravitationally bound structures in the observable universe. Galaxy clusters are assemblages of hundreds to thousands of individual galaxies, bound together by their collective gravity and embedded in an enormous halo of dark matter that extends far beyond the visible galaxies. But what makes clusters so important for black hole physics is not the visible galaxies themselves. It is the hot, diffuse gas that fills the space between those galaxies. This intracluster medium, as astrophysicists call it, is a vast ocean of plasma heated to temperatures of tens of millions to hundreds of millions of degrees. It is so hot that it glows in X-rays rather than visible light, and it represents the majority of the normal matter content of many galaxy clusters, outweighing the stars in the cluster galaxies by a factor of roughly 5 to 10. For the jets emerging from J1007 plus 3540's reborn central engine, this intracluster medium represents an enormous obstacle. The jets are trying to push their way outward through a medium that is extremely dense by the standards of intergalactic space, creating a pressure that resists their expansion and can bend, compress, and redirect their flow. The LOFAR images of J1007 plus 3540 capture this struggle in striking detail. The northern lobe of the jet structure is dramatically compressed compared to the southern lobe, its normal elongated shape flattened and distorted by the particularly dense medium it is pushing through in that direction. The plasma that has been shunted sideways by the cluster gas has formed a curved, swept-back morphology that reveals the direction and intensity of the environmental pressure. In the UGMRT data, this compressed northern region shows an ultra-steep radio spectrum, meaning the ratio of emission at different frequencies indicates that the particles there are very old and have lost most of their initial energy, a consequence both of their age and of the enhanced energy losses they experience in the high-pressure cluster environment. There is also a long, faint tail of radio emission, extending to the southwest of the main jet structure, a tendril of old plasma dragged through the cluster over millions of years by the relative motion of the galaxy through its cluster environment. This tail, extending for hundreds of thousands of light-years in its own right, is a reminder that J1007 plus 3540 is not a stationary object. It is moving through the cluster, carried along by the gravitational dynamics of the cluster itself, and that motion leaves a wake in the diffuse plasma of previous eruptions that we can trace in low-frequency radio images. Team member Sabyasachi Pal, also of Midnapore City College, described J1007 plus 3540 as one of the clearest and most spectacular examples of episodic AGN with jet cluster interaction in the observational literature, where the surrounding hot gas bends, compresses, and distorts the jets into the complex morphology we see in the images. The word episodic here is important, because it points to a broader truth about how black holes behave over cosmic time. J1007 plus 3540 is not an anomaly. It is an illustration of a pattern. Black holes at the centers of galaxies do not simply switch on once and stay on, or switch on once and then permanently off. They cycle, they pulse. They turn on, exhaust their fuel or blow it away, fall quiet, and then, given new fuel by some later event, turn on again. This cyclical behavior, episodic AGN activity as it is called in the technical literature, is now recognized as a fundamental aspect of how massive black holes coexist with and influence the galaxies they inhabit. The feedback loop between a black hole and its host galaxy is not a one-way street. The black hole feeds on material from the galaxy, but its activity also affects the galaxy, heating and stirring the gas that might otherwise cool and form new stars, driving outflows that can carry gas out of the galaxy entirely, and in some cases even suppressing its own feeding by blowing away the very material it would otherwise consume. This self-regulation means that periods of intense activity are naturally followed by periods of quiet, during which the gas that was blown away gradually returns or cools back down, eventually triggering the next episode of feeding. J1007 plus 3540 is a particularly vivid illustration of this cycle, because the two distinct generations of plasma emission, separated by the 100 million year dormancy, allow astronomers to actually measure the timescales involved. How long does it take for a galaxy cluster environment to recover from a major episode of AGN activity? How long before enough gas cools and collects at the galactic center to refuel the black hole? The 100 million year gap in J1007 plus 3540 provides one data point in answering these questions. Other systems with multiple generations of plasma will provide others, and as the statistical sample of well-characterized episodic AGN grows, theorists will be able to build and test models of how these cycles regulate galaxy evolution across cosmic time. Astronomer Vivian Yu, who was asked to comment on the significance of the J1007 plus 3540 findings for Scientific American, noted that these observations help us understand that the relationship between a galaxy's jets and the cluster environment is very dynamic. The word dynamic here carries a lot of scientific freight. It means not just that things change over time, but that the changes are governed by complex nonlinear interactions between multiple physical processes operating on a vast range of spatial and temporal scales simultaneously. The jets affect the cluster gas affects the jets. The changes in the cluster gas affect how well the galaxy can cool and form stars, which affects how the black hole gets fed in the future, which affects the next episode of jet activity. It is a feedback loop that operates across billions of years of cosmic history. And here is where the stories of Ansky and J 1007 plus 3540, though physically very different in their details and scales, converge on a common theme that strikes at some of the most profound questions in modern astrophysics. Both of these awakening black holes are reminding us that the universe is not a static backdrop for interesting events. It is a dynamic system in which the most massive and energetic objects undergo cycles of activity and rest that shape everything around them, from the distribution of gas in a galaxy cluster to the formation rate of stars in individual galaxies to the long-term evolution of structure across cosmic time. The quiet black holes we observe today in most galaxies around us, including our own, are not permanently quiet. They are dormant, waiting, between episodes of activity. And the episodes of activity, when they come, reverberate across the cosmos in ways we are only beginning to fully understand. The question of what triggers these awakenings, what tips a dormant system into an active one, is one of the central open problems in the study of galaxy evolution. For Ansky, the answer remains genuinely unclear. The optical brightening in 2019 might reflect a tidal disruption event that initiated accretion, or it might reflect the delivery of gas to the galactic center through some other mechanism, perhaps the slow infall of cooling gas from a hot halo, perhaps a minor merger with a smaller satellite galaxy that disturbed the gas distribution. The absence of a clear tidal disruption event signature, combined with the persistence and the spectral properties of the ongoing variability, points more toward a general activation process than a single discrete event. But the evidence does not definitively rule out any of the main scenarios, and researchers are continuing to gather data that may eventually resolve the ambiguity. For J1007 plus 3540, the trigger for the reactivation after 100 million years of dormancy is equally uncertain. The presence of the system in a massive galaxy cluster with a hot intracluster medium suggests that cooling gas from that medium may have eventually deposited enough material at the galactic center to restart the feeding. This process, called cooling flow or cool core accretion, is thought to be a significant driver of AGN activity in cluster central galaxies. But cluster mergers, galaxy-galaxy interactions within the cluster, and secular dynamical processes within the galaxy itself are all also plausible contributors, and distinguishing between them requires detailed observations of the large-scale gas distribution and dynamics that go beyond what the radio images alone can tell us. What both stories share, what makes them genuinely landmark events in the observational study of black holes, is not just their individual scientific content, but what they represent for the future of the field. We are, right now, at the beginning of a new era in multi-messenger astronomy, an era in which we can observe the universe simultaneously in gravitational waves, in photons spanning the full electromagnetic spectrum from radio to gamma rays, in neutrinos, and increasingly in time-domain surveys that track how objects change over hours, days, months, and years. The combination of these observational capabilities is opening windows on phenomena that were simply invisible to earlier generations of astronomers. Ansky is a perfect example of what this new era makes possible. The optical brightening in 2019 was caught by the Zwicky Transient Facility's Time Domain Survey, a telescope specifically designed to monitor the sky repeatedly and flag changes in the brightness of individual objects. Without that kind of systematic, repeated monitoring of hundreds of millions of sources, the initial activation would have been invisible. The X-ray eruptions in 2024 were caught by a combination of X-ray telescopes that had been triggered to monitor the galaxy based on the prior optical discovery. And the subsequent detailed characterization of the QPE properties, the timing, the spectral evolution, the changing burst profiles, required the coordinated deployment of multiple specialized instruments spanning 2 space agencies and multiple observatories. This is modern observational astronomy at its best, a global network of telescopes, operated by multiple agencies and institutions across multiple countries, working together to observe a single extraordinary object in multiple wavelengths, simultaneously and over extended periods of time. No single instrument could have told this story. The story required all of them, and the ability to combine their data coherently, to weave the optical monitoring from the Zwicky facility with the X-ray observations from XMM-Newton and NICER and Chandra and Swift into a single coherent narrative speaks to the power of collaborative multi-wavelength science. But there is a dimension to the story of awakening black holes that we have not yet fully explored, one that connects these visible eruptions to an even deeper and more fundamental layer of physical reality. The same processes that produce the X-ray flares of Ansky's quasi-periodic eruptions, the inspiral of a compact object toward a massive black hole, also produce another kind of emission entirely, one that does not travel as electromagnetic radiation, one that we cannot see with any telescope no matter how sensitive, one that passes through ordinary matter as if it were not there, gravitational waves, and when we follow that thread, the story of these awakening black holes takes on a dimension that connects them to one of the great frontiers of 21st century physics. To understand this connection, we need to step back and think about what an extreme mass ratio inspiral actually is at the deepest physical level. In Einstein's general theory of relativity, gravity is not a force in the traditional Newtonian sense. It is a consequence of the curvature of space-time produced by massive objects. Matter tells space-time how to curve, and curved space-time tells matter how to move. When two massive objects orbit each other, their accelerating masses continuously generate ripples in the fabric of space-time, oscillating distortions that propagate outward at the speed of light. These are gravitational waves. For ordinary binary star systems, the gravitational waves produced are incredibly faint, requiring extraordinarily sensitive instruments to detect even nearby events. The LIGO and Virgo detectors on Earth, with their multi-kilometre-long laser interferometer arms, are sensitive enough to detect gravitational waves from merging stellar mass black holes and neutron stars in the final moments before their collision. But these ground-based detectors operate at frequencies of tens to thousands of hertz, which corresponds to the gravitational wave frequencies produced by compact object mergers in the final seconds to minutes before coalescence. Extreme mass ratio inspirals produce gravitational waves at much lower frequencies, in the millihertz range, frequencies that correspond to orbital periods of minutes to days, rather than the sub-second periods of merging compact objects. These millihertz gravitational waves pass completely undetected by LIGO and Virgo, which have no sensitivity at such low frequencies because seismic noise from the Earth itself overwhelms any signal at those timescales. To detect millihertz gravitational waves, you need a detector in space, far from geological activity, ocean waves, and human civilization. That detector is LISA, the Laser Interferometer Space Antenna. Planned as a joint mission of the European Space Agency and NASA, LISA will consist of 3 spacecraft flying in a triangular formation, each separated from the others by approximately 2.5 million kilometers, connected by laser beams. As gravitational waves pass through this triangle of spacecraft, the distances between them will oscillate by tiny fractions of the laser wavelength, and by measuring those oscillations with extraordinary precision, LISA will map the gravitational wave universe in the millihertz frequency band for the first time. LISA is expected to launch in the mid-2030s, and among its primary science targets are extreme mass ratio inspirals, exactly like the system hypothesized to be driving Ansky's quasi-periodic eruptions. An EMRI, in which a stellar mass compact object spirals toward a million solar mass black hole, would produce a continuous gravitational wave signal in the millihertz band that LISA could potentially detect and characterize in extraordinary detail, measuring the masses and spins of both objects, the orbital eccentricity and inclination, and the rate of orbital decay due to gravitational wave emission, all from the gravitational wave signal alone. But the QPE observations of Ansky add something crucial to this picture. They provide an electromagnetic counterpart. If the same physical system that produces the X-ray eruptions also produces gravitational waves detectable by LISA, then we have the prospect of true multi-messenger astronomy at the millihertz scale, simultaneously seeing the X-ray eruptions with orbital telescopes and feeling the gravitational wave oscillations with LISA, 2 completely independent observational channels telling us about the same system from completely different physical perspectives. ESA researcher Erwan Quintin explicitly noted this connection when discussing the Ansky findings, emphasizing that the X-ray observations of QPEs like Ansky are crucial for complementing future gravitational wave data and helping to solve the puzzling behavior of massive black holes. This is not just a technical point. It represents a profound philosophical shift in how we study some of the most extreme phenomena in the universe. When we can observe the same event in gravitational waves and in electromagnetic radiation simultaneously, the two sets of observations constrain each other in ways that neither could achieve alone. The gravitational wave signal tells you precisely about the orbital mechanics and the masses involved. The electromagnetic signal tells you about the accretion disk, the plasma physics, the radiative processes that transform the orbital energy into observable radiation. Together, they offer a complete portrait that neither messenger could provide individually. There is even a remarkable additional possibility that some researchers have raised. If QPS are indeed electromagnetic counterparts to EMRs, then future joint observations combining LISA gravitational wave detections with X-ray observations of QPE hosts could be used to measure the expansion rate of the universe through an independent method. The gravitational wave signal provides what cosmologists call a standard siren measurement of the luminosity distance to the source, while the host galaxy identification from the electromagnetic counterpart provides the redshift. Combining distance and redshift gives a measurement of the Hubble constant, the rate at which the universe is expanding, at a time when there is a genuine and unresolved tension between different existing methods of measuring this fundamental quantity. Any independent new probe is enormously valuable to cosmology. So the story of Ansky, which began with a simple automated alert from a sky survey camera, noting that a distant galaxy had unexpectedly brightened in late 2019, now threads through some of the deepest and most actively contested questions in modern physics and cosmology. What triggers black hole awakening? How do accretion disks form and evolve around newly active black holes? What is the physical mechanism behind quasi-periodic eruptions? How do extreme mass ratio in spirals produce electromagnetic signals alongside their gravitational wave emission? And how do we use joint observations across multiple physical messengers to probe the cosmos in ways that were impossible for any previous generation of astronomers? These are not niche questions of interest only to narrow specialists. They are questions about the engines that helped shape the universe we inhabit, the black holes that governed the flow of gas in galaxies, the feedback processes that determined how much material could cool and form new stars and new solar systems over billions of years of cosmic history. Every black hole that wakes up, every accretion disk that assembles itself from the gas of a dormant galaxy, every burst of X-ray radiation that travels 300 million light-years to trigger an automated alert in a sky survey is a window into those deep and ancient processes, and we are, at this precise moment in the history of science, standing at the threshold of being able to look through that window more clearly than any previous generation could ever have dreamed. Consider the full arc of what we have been describing, and let us take a moment to appreciate the deep strangeness of the situation before we dive back into the details. A galaxy 300 million light-years away in the direction of Virgo, catalogued as ordinary and unremarkable, is watched for years by automated survey telescopes without producing a single interesting alert. Then, in December of 2019, it brightens. Not dramatically at first, not in a way that would make headlines, just a quiet, persistent elevation in its nuclear brightness that tells careful observers something has changed in the very center of that galaxy. For 4 years it simmers, flickering and varying in optical light, hinting at activity without revealing its full nature, and then, in February of 2024, it erupts in X-rays with a violence and regularity that has no precedent in the observational record. That is the timeline of Ansky. And from the perspective of astrophysics, the 4 years between the optical brightening and the X-ray eruptions may themselves be telling a deep story about how black holes wake up, a story that goes well beyond the dramatic headline of the eruptions themselves. Think about what those 4 years represent. The optical brightening in 2019 almost certainly marks the moment when material first began falling onto the newly forming accretion disk in significant quantities, or possibly the moment when a stellar disruption provided a sudden reservoir of infalling gas. But the X-ray emission that would mark the disk as hot and densely accreting did not appear for years afterward. There are plausible physical reasons for this delay. When an accretion disk forms for the first time, or reforms after a long period of dormancy, it may initially be cool and extended, with material settling into circular orbits at large radii from the central black hole, before viscous processes and magneto-hydrodynamic instabilities can drive it inward toward the hotter, denser inner regions where most of the X-ray emission originates. As the disk matures and the inner regions build up in density and temperature, the X-ray luminosity rises. The disk also needs time to develop the organized magnetic structure that drives accretion, a process governed by the magnetorotational instability, one of the most important mechanisms in theoretical astrophysics. In a purely hydrodynamic disk without magnetic fields, the angular momentum transport needed to allow gas to spiral inward would be negligible, and accretion would be impossibly slow. But with magnetic fields threading the disk, a powerful turbulence develops that efficiently transfers angular momentum outward and allows mass to flow inward, and this process takes time to reach a mature, steady-state configuration from an initially quiet, field-free starting point. The 4-year delay between optical brightening and X-ray eruptions in Ansky may therefore be a window into the disk formation and maturation process itself, a timescale measurement of how long it takes for a newly assembled accretion disk around a million solar mass black hole to develop the inner hot region and the orbital architecture that can produce QPS. This is not a measurement that theorists have been able to make before, because no previous system offered both the clear baseline of prior inactivity and the sequential observations covering both the optical activation and the subsequent X-ray eruptions. Ansky is providing data that simply did not exist before. The mass of the central black hole also plays a role in interpreting these timescales. At approximately 1 million solar masses, Ansky's black hole is relatively light for a supermassive black hole. The innermost stable circular orbit around a non-spinning 1 million solar mass black hole, the innermost point at which material can orbit before inevitably plunging inward, corresponds to a physical size of a few million kilometers, or a few % of the distance between Earth and the Sun. The viscous timescale, the time it takes for angular momentum transport to drive material from the outer regions of the disk to this inner edge, scales with the mass of the black hole and the size of the disk. For a disk of the size implied by the optical brightening and the QPE properties, these timescales work out to months to years, consistent with the observed delay. This is the kind of detailed, physically specific prediction that makes observational astrophysics so powerful. The theory does not just say something will happen, it says roughly when it will happen, and gives specific reasons why. When the observations match the predicted timescales, that is not just a successful prediction, it is a measurement of the underlying physical parameters of the system. And when the observations deviate from the predictions, as they do in various details of Ansky's behavior, those deviations point toward additional physics that the simpler models are missing. We should also spend a moment thinking carefully about what the X-ray spectrum of Ansky's eruptions is telling us beyond the broad brush picture of a hot accretion disk. The study of X-ray spectra from active black holes is one of the most technically demanding and theoretically rich areas of modern astrophysics, because the spectrum encodes information about multiple physical processes happening simultaneously in the innermost region of the accretion flow. The soft X-ray emission that dominates during the peak of each QPE burst, centered around a few tenths to a few kilo electron volts, is consistent with thermal emission from a region of plasma at temperatures of tens of millions of degrees. This thermal component can be modelled as a modified blackbody or as emission from a hot plasma of specific temperature, and the evolution of this component's temperature and luminosity through the rise, peak and decay of each burst tells you how the temperature and the size of the emitting region are changing. If the emitting region heats up as it is compressed by the shock and then cools as the shocked material expands and is pushed away from the collision site, the spectral evolution should show the characteristic signature of a specific cooling process, whether the plasma cools primarily by radiating photons or by expanding adiabatically against the surrounding disk material. In Ansky's case, the spectral evolution is complex and time-varying in ways that reveal additional physics. The Bassini profile signatures identified by Joeen Chakraborty and collaborators, in which the spectrum shows both emission from hot material and absorption from cooler material moving toward the observer, suggest that the shock generates not just a hot spot, but an outflowing wind of partially ionized material that partially reabsorbs the emitted X-rays as they travel outward. This is a physically detailed picture that constrains the outflow velocity, the ionization state of the ejected material, and the geometry of the emission region relative to the disk plane. The fact that these absorption features change in their central wavelength, width, and depth over the course of each individual eruption, evolving systematically from the onset of the burst through the peak and into the decay, is a level of spectral detail that has not been seen before in any QPE system. It is possible only because Ansky's eruptions are so luminous and so long-lasting that the signal-to-noise ratio accumulated during a single burst is high enough to support time-resolved spectroscopy, analysing the spectrum not just as an average over the full burst but as a sequence of snapshots showing how the spectral properties change minute by minute. This time-resolved spectroscopy is one of the most powerful tools in the arsenal of X-ray astronomers, and its application to Ansky's eruptions is producing a level of physical detail about black hole accretion in action that was not achievable with any previous QPE source. The UV emission from Ansky, which researchers report detecting at low but statistically significant levels during the eruptions, adds yet another layer to the picture. Ultraviolet photons are emitted by material that is cooler than the X-ray emitting plasma, but still far hotter than ordinary stellar surfaces, with temperatures of hundreds of thousands of degrees. This UV emission likely originates from the outer regions of the disk that are being irradiated and heated by the X-ray burst from the inner collision site, a process called reprocessing, in which the hard X-ray photons are absorbed by the disk material and re-emitted at softer UV wavelengths. The fact that UV variations associated with the QPEs have been detected at all in Ansky is notable, because in other QPE systems the disk radii are small enough and the UV emission faint enough that such variations have not been clearly identified. Ansky's longer recurrence timescale and the larger disk radius implied by that timescale mean that the reprocessing signal, originating from a larger disk surface area, is more easily detectable. Tracking the UV variations in detail, comparing their timing and amplitude to the X-ray burst profiles, can in principle reveal how the disk responds to the repeated energetic events of the eruptions, whether the disk is building up energy between bursts and releasing it in the eruptions themselves, or whether the disk is primarily a passive reprocessor of energy generated by a separate mechanism. These are testable distinctions, and the multi-wavelength observations of Ansky that are ongoing will eventually accumulate enough data to make them. The theoretical community's response to Ansky has been rapid and energetic, which is itself a sign of how significant the discovery is considered to be. Within weeks of the Nature Astronomy paper's publication in April 2025, multiple groups had posted theoretical analyses and model calculations to the ARXIV preprint server, each proposing explanations for the extreme properties of Ansky's QPEs and making predictions about future behavior. Some groups focused on the EMRI disk collision model and worked out detailed predictions for how the burst properties should evolve if the orbiting compact object's orbit is decaying under gravitational wave emission. Others explored models in which the eruptions are driven by mass transfer from a companion object onto an accretion disk, analogous to the outbursts seen in X-ray binary systems, but scaled up to the supermassive regime. Still others examined the possibility that the QPEs are produced by a different mechanism entirely, perhaps a disk instability analogous to the thermal viscous instabilities that drive outbursts in cataclysmic variable star systems. None of these models has yet achieved a complete and self-consistent explanation for all of Ansky's observed properties simultaneously. The extraordinary energy of the bursts, the very long recurrence timescale, the specific shape of the burst profiles, the UV variations, and the systematic evolution between 2024 and 2025 all need to be explained by a single coherent physical picture. Currently, different models can explain different subsets of these properties, but no single model accounts for all of them. This is precisely the kind of situation that drives theoretical progress. The observations are specific enough to rule out simplified models, while the problem is tractable enough that improved models can be constructed and tested. What makes this theoretical landscape particularly interesting is that different models make specific and divergent predictions about Ansky's future behavior. The EMRI disk collision models predict that the recurrence time should eventually begin to shorten as the gravitational wave in spiral dominates over any disk evolution effects, and that the burst properties should evolve in a specific way as the orbital radius decreases. Disk instability models predict a different kind of evolution, perhaps a more stochastic or quasi-periodic modulation of the burst properties related to the thermal state of the disk, rather than to orbital mechanics. Mass transfer models predict evolution connected to changes in the mass transfer rate from the companion, which itself might be tied to the orbital evolution. Years of continued monitoring of Ansky will provide data that distinguishes between these models, not by finding a smoking gun proof of any one of them, but by accumulating enough evolution of the system's properties to rule out some models and place increasingly tight constraints on others. This is how theoretical questions in astrophysics are typically resolved. Not through a single decisive observation, but through the gradual accumulation of a body of data that is collectively inconsistent with all but one or a few of the competing theoretical frameworks. And it is worth pausing here to note something that gets lost in the excitement of discovery announcements. This resolution will take years, possibly decades. The monitoring campaigns required to definitively distinguish between the competing QPE models for Ansky require observational baselines of many years, requiring continued operation of XMM-Newton and NISA and their successors. The theoretical work required to build models that are physically detailed enough to make specific quantitative predictions about time-resolved spectral evolution and long-term burst property trends is also years in the making. Science operates on timescales that do not fit naturally into news cycles, and the full scientific payoff of the Ansky discovery will unfold over a timeline that stretches across years and decades, not weeks and months. I find that fact more exciting than frustrating, because it means that this is a genuinely open story. Every new observation of Ansky that is published adds to a narrative that is still being written. Every theoretical paper that proposes a model or tests a prediction against existing data is part of a conversation that is still ongoing, and the eventual resolution, the moment when the scientific community reaches a sufficient consensus about what is actually happening in the nucleus of that galaxy 300 million light-years away, will be a genuine landmark in our understanding of black hole physics. Let us now return to the J1007+3540 system and think more carefully about what its dormancy period can teach us about the long-term behavior of supermassive black holes over geological timescales. 100 million years is not an unusual dormancy period for a radio galaxy, although it is certainly on the longer end of the distribution of known episodic AGN systems. Studies of double-double radio galaxies, systems where two distinct generations of jet emission have been identified, suggest that dormancy periods between episodes of activity can range from tens of millions to hundreds of millions of years. The physical processes that determine how long a black hole remains dormant after one episode of activity and before the next one begins are not yet well understood quantitatively, but they are thought to be related to how efficiently the previous episode of AGN feedback heated the surrounding gas and suppressed the subsequent cooling that would have provided new fuel. In a simple picture, you might expect a tight correlation. A more powerful AGN episode injects more energy into the cluster gas, which takes longer to cool back down, which leads to a longer dormancy period before the next episode. But the real situation is more complex because the geometry of the heating matters as much as its total energy. Jets that deposit their energy in concentrated regions of the cluster may leave cool gas in other parts of the cluster that continues to feed the black hole even while the heated regions are still radiating. The circulation patterns in the intra-cluster medium, driven by the combination of cooling, heating, and bulk motions of the cluster gas, determine where cold gas accumulates and how quickly it can reach the galactic center. For J1007+3540, the 100 million year dormancy period represents a specific combination of AGN feedback efficiency and cluster cooling rate. The fact that the previous episode produced the ancient lobes we see in the LOFAR images, whose estimated age of 240 million years gives us the timing of the original eruption, means that we can in principle trace the causal chain. The ancient eruption heated the cluster gas. Cooling took approximately 100 million years to re-establish cold inflows sufficient to trigger a new episode, and then the new jets ignited roughly 140 million years ago. This timeline is a direct observational measurement of the AGN feedback cycle in a real galaxy cluster. It is the kind of measurement that galaxy evolution theorists use to calibrate their models of AGN feedback and its effects on cluster evolution. And J1007+3540's particular combination of large jet scale, strong cluster environmental effects, and clear two-generation morphology makes it an especially valuable calibration point. It is also worth noting what J1007+3540 is telling us about the environmental effects of AGN activity at the larger scales. The million light-year extent of the current jet structure means that the energy being deposited by the reborn jets is being spread across a volume of space that encompasses not just the host galaxy, but a significant fraction of the surrounding cluster. The bent and distorted morphology of the jets, sculpted by the cluster medium, means that the energy is being deposited in a distributed way, heated gas being pushed and stirred and circulated throughout the cluster volume, rather than deposited in a single concentrated region. This kind of distributed heating is exactly what theoretical models of AGN feedback require to explain why massive galaxy clusters do not cool catastrophically and form stars at rates orders of magnitude higher than observed. The hot gas in a massive cluster would, if left to cool without any heating source, radiate away its thermal energy in a time of tens to hundreds of millions of years, forming a cooling flow that would dump enormous quantities of cold gas onto the central galaxy. The observed star formation rates in cluster central galaxies are typically only a few % of what unimpeded cooling would predict. Something is preventing most of the gas from cooling, and the most widely accepted explanation is AGN feedback, with the jets providing the distributed heating that offsets the radiative cooling across the cluster volume. J1007 plus 3540 is showing us this process in action. The reborn jets are injecting energy into the cluster medium. That energy is being thermalized by the shocks and turbulence associated with the jet-cluster interaction, heated up and distributed through the intracluster gas. The specific morphological details of how the jets are bending and the lobes are compressing reveal information about the local pressure gradients and density structure of the cluster medium, which in turn can be compared to X-ray observations of the hot gas distribution to build a complete three-dimensional picture of the feedback in progress. In the context of all that we have discussed, I want to offer a broader reflection on what these awakening black holes mean for our understanding of the long arc of cosmic history. We tend to think of the universe's history as a story of gradual cooling and quieting. The earliest epochs after the Big Bang were extraordinarily energetic, temperatures of billions of degrees, primordial nucleosynthesis forging hydrogen and helium, the universe itself opaque to light until a few 100,000 years after the beginning, when electrons and protons combined into neutral hydrogen and the cosmic microwave background was released. Then the Dark Ages, a long period of relative quiet before the first stars ignited. Then the epoch of reionization, as those first stars and the first active black holes flooded the universe with ultraviolet photons. Then the peak of star formation and AGN activity around 10 billion years ago. And then the gradual decline as the universe aged. Galaxies used up their gas, star formation rates dropped, and the most energetic AGN faded. In this narrative, the universe today is quieter than it was in its youth. And that is broadly true as a statistical statement. The density of quasars in the universe today is vastly lower than it was at the epoch of peak AGN activity. The total rate of star formation across all galaxies today is much lower than it was several billion years ago. The universe is indeed in a calmer phase of its evolution compared to the tumultuous early period of galaxy formation. But calmer is not the same as quiet. The stories of Ansky and J1007 plus 3540 are reminders that the universe, even in this late calmer epoch of its evolution, continues to be punctuated by dramatic events on the scale of individual galaxies and galaxy clusters. Black holes that have been sleeping for tens or hundreds of millions of years still wake up. When they do, they reshape their environments dramatically, injecting energy that influences star formation and gas distribution across scales of millions of light years. These events are not relics of an earlier, more active epoch. They are happening now, around us, in the local universe, on timescales accessible to human observation. This perspective has a subtle but important implication for how we model galaxy evolution. If a significant fraction of apparently dormant black holes are capable of reactivating on timescales of tens to hundreds of millions of years, then the cumulative effect of these reactivation events on the long-term evolution of galaxy clusters could be substantial even in the current epoch. Each reactivation event injects a burst of energy into the cluster medium, resets the cooling clock, and reshapes the distribution of hot gas. Over tens of billions of years of cosmic evolution, these episodic bursts may account for a significant portion of the total AGN feedback energy that has prevented massive galaxies from overcooling. Understanding the rate, duration, and energy of episodic reactivation events like the one we are witnessing in J1007 plus 354 is therefore not just interesting for its own sake, but is a necessary input to models of long-term galaxy evolution. The observational frontier here is daunting but exciting. We currently know of only a handful of well-characterized episodic AGN systems, where the dormancy period and the properties of multiple generations of jet activity can be measured. The existing radio survey data, obtained with instruments like the Very Large Array, LOFAR, and the Giant Meter Wave Radio Telescope, has revealed the morphologies of many radio galaxies, but with sensitivities that often miss the faint ancient plasma from previous episodes of activity. The next generation of radio observatories, particularly the Square Kilometre Array, will be sensitive enough to detect the ultra-faint steep spectrum plasma from even the oldest and most energetically depleted previous eruptions, potentially revealing the full multi-episode histories of radio galaxies in unprecedented detail. And as we close this exploration of awakening black holes, I want to leave you with a thought that I find both humbling and genuinely inspiring about the work we have been discussing. Every observation we have described in this documentary required human beings to make difficult choices. Scientists had to advocate for telescope time, competing with hundreds of other researchers who also had important targets they wanted to observe. Engineers had to maintain aging instruments years beyond their designed lifetimes because the scientific returns justified the operational costs. Funding agencies had to make long-term commitments to observational programs whose payoffs could not be precisely predicted in advance. Graduate students and postdoctoral researchers had to spend years developing the data analysis techniques needed to extract reliable results from complex multi-instrument datasets. And the researchers who wrote the papers and published the results had to navigate the peer review process, responding to critical questions from expert referees who pushed them to be more rigorous, more careful, more complete in their interpretations. None of this is glamorous work in the way that public descriptions of scientific discovery often suggest. It is laborious, painstaking, frequently frustrating, and punctuated by the occasional extraordinary moment when the data reveals something genuinely new and unexpected. The extraordinary moments make the headlines. The laborious work in between makes the extraordinary moments possible. When Lorena Hernández-García's team looked at the NICER data in February 2024 and first saw the regular X-ray burst from Ansky, that moment of recognition did not come from nothing. It came from years of monitoring a galaxy that most of the astronomical community would have considered a low-priority target. It came from the careful archival work done by Paula Sanchez-Saez's team years earlier that established the baseline of prior inactivity and documented the initial optical brightening. It came from the existence of instruments that had been built, tested, launched, and maintained by hundreds of engineers and scientists over decades. The discovery of Ansky is, in this sense, a product of the entire infrastructure of modern astronomy, not of any single inspired individual, and that infrastructure is itself a product of a collective decision made implicitly by many societies over many decades to invest in the fundamental scientific enterprise of understanding the universe we inhabit. The returns on that investment are not measured in economic productivity, or national security, or technological innovation, although those returns sometimes follow from basic scientific discoveries in unexpected ways. The primary return is knowledge, understanding, the expansion of human awareness of what exists and how it works. And when we watch a black hole wake up after 100 million years of silence, we're collecting on that investment in a form that no economic metric can capture. The experience of genuine discovery, of knowing something true about the universe that no human being knew before. 300 million light-years away, a million solar mass black hole is erupting in X-rays every few days, spiraling deeper into activity while a small compact object dances around its accretion disk. 100 million years of dormancy ended with jets that now carve through a galaxy cluster, on a scale 10 times the width of our own galaxy. These are facts about the actual universe, verified by careful observation and honest science, earned by decades of investment and sustained effort. In the end, that is what makes the story of these awakening black holes so worth telling and so worth understanding. Not the drama of the headline, though the drama is real. Not the impressive numbers, though the numbers are staggering. But the fact that patient, careful, collaborative science has allowed a species that evolved on one small planet to know, with genuine confidence, what is happening in the nucleus of a galaxy 300 million light-years away, in the deep silence between the stars of a cluster of galaxies that our ancestors could not even have imagined existed. That is extraordinary. That is what science does, and we are lucky to live in the moment when it is doing it this well, one that goes to the heart of how we think about the co-evolution of black holes and galaxies. The standard picture of galaxy evolution includes a phase in which the central black hole grows rapidly, by accreting large quantities of gas, often during or after a major galaxy merger that funnels gas to the nucleus. This active phase corresponds to what we observe as quasars, or powerful active galactic nuclei in distant galaxies. Eventually, the black hole either exhausts the available fuel or blows it away through its own feedback, and it settles into a dormant state. Over subsequent billions of years, it sits quiet while the galaxy evolves around it, until some new event triggers another episode of activity. In this picture, the dormancy of most nearby black holes reflects the fact that the major merger events that triggered the most intense growth phases happened billions of years ago, and the galaxies in our local universe are now in a quieter evolutionary phase. But quieter does not mean permanently quiet. Galaxy interactions continue to occur, gas continues to cool from hot halos, and secular instabilities continue to channel material toward galactic centers. And sometimes, something tips a dormant black hole back into activity on a timescale that is not billions of years, but merely tens of millions of years, or millions of years, or in the case of Ansky, apparently just a few years from the first optical signs to full X-ray eruptions. What Ansky teaches us about this process is that the awakening can be dramatic and rapid, at least by cosmic standards. The black hole does not need years of gradual brightening across all wavelengths before something genuinely extreme happens. It can jump from optical brightening to extraordinary X-ray eruptions within a few years of first showing signs of life. This rapidity has implications for how common such events might be in the universe at any given time, for how many galaxies around us might be in the early stages of such an awakening right now, and for how often our all-sky monitoring program should expect to catch them. The statistical question is deeply interesting. The Zwicky Transient Facility monitors hundreds of millions of galaxies. Events like the initial Ansky brightening, a nuclear optical transient that persists and evolves over years, occur at some rate per galaxy per unit time. As the community examines more carefully the properties of nuclear optical transients in Zwicky survey data, they are finding an increasing number of events that may represent similar activations of dormant black holes, each at a somewhat different stage of the process and with somewhat different properties, depending on the mass of the central black hole, the nature of the triggering event, and the properties of the surrounding stellar and gas environment. In this sense, Ansky is not just a single unique event, it is the prototype for a new class of objects that the next generation of sky surveys, including the Rubin Observatory's legacy survey of space and time, which began full science operations in 2025, will find in potentially large numbers. Each new example will add constraints, will show whether the 4-year delay is typical or unusual, whether the extreme QPE properties are representative or a coincidence of specific parameters in this particular system, and whether the evolution of the burst properties from 2024 to 2025 follows a pattern that appears repeatedly across many systems or is specific to Ansky's individual history. I think it is worth pausing here and reflecting on something that rarely gets discussed in science documentaries, but that I find genuinely important to acknowledge on this channel. The discovery of Ansky, the discovery of J1007 plus 354O's volcanic reawakening, these are achievements not just of technology and technique, but of sustained human effort and institutional commitment over many years and across many countries. The Zwicky Transient Facility, which caught the initial brightening of Ansky in 2019, is operated by Caltech and a consortium of international partners. The XMM-Newton Observatory, which provided the crucial X-ray characterization of the QPEs, was designed and built by ESA with contributions from multiple European national space agencies and has been operating in space since 1999. NASA's NICER instrument is the product of years of engineering work at Goddard Space Flight Center and dozens of partner institutions. Chandra, launched also in 1999, is operated by the Smithsonian Astrophysical Observatory under a NASA contract that has sustained it in operation for more than a quarter century. These instruments do not exist because of any single decision or any single individual. They exist because of a community of scientists and engineers and administrators who collectively advocated for them, designed them, built them, launched them, operated them, and kept them running long past their original design lifetimes, because their scientific value continued to justify the investment. The discovery of Ansky is, in a very real sense, the product of the cumulative scientific and engineering effort of thousands of people spanning multiple decades. When Lorena Hernández-García's team published their Nature Astronomy paper, In April 2025, the headline belonged to their analysis and interpretation, but the data that made that analysis possible belonged to a much larger community. This matters, I think, because it is a reminder of what science actually is as a human enterprise. It is not a collection of individual brilliant insights, though individual brilliance certainly contributes. It is a sustained collective process, built on infrastructure that takes generations to construct, maintained by institutional commitments that span decades, and advancing through the cumulative effort of many people working on different pieces of an enormous puzzle. Every dramatic discovery like Ansky represents the visible tip of an iceberg of sustained, often unglamorous work that created the conditions for the discovery to be possible. Now let us return to the physics and to some of the deeper questions that both Ansky and J1007 plus 354 are raising about the nature of black holes themselves. One of the most profound and under-discussed aspects of the awakening black hole phenomenon is what it tells us about the relationship between black hole mass and the properties of the activity that emerges when a dormant system begins to feed. Ansky's black hole is approximately 1 million solar masses. That puts it in the lower range of supermassive black holes, roughly the mass of the black holes that sit at the centres of the Milky Way or M31. The QPEs it produces are extraordinary by the standards of QPAs from other known systems, but they are occurring in the context of a modest central mass. The timescales of the eruptions, the day-and-a-half to 4-day durations and the 4 to 10-day recurrence periods, are related to orbital periods around a black hole of this specific mass. For comparison, J1007 plus 3540's central black hole is likely much more massive, potentially hundreds of millions to billions of solar masses based on its jet power and the properties of the galaxy cluster it inhabits. The kinds of accretion activity and jet production seen in massive radio galaxies like J1007 plus 354 operate on correspondingly longer timescales and larger physical scales. The 100-million-year dormancy period and the million-light-year jet structures are features of a fundamentally different mass regime than Ansky's QPE bursts. This mass scaling is a general and important principle in black hole physics. Almost every timescale associated with accretion, every physical length scale associated with the disk and jets, every energy scale associated with the radiation produced, all scale with the mass of the central black hole in predictable ways. The gravitational radius, the fundamental length scale of a black hole, is directly proportional to its mass. The orbital period at the innermost stable orbit scales as the mass. The accretion timescale scales as the mass. So a system like J1007 plus 3540, with a black hole perhaps 1,000 times more massive than Ansky's, operates on characteristic timescales 1,000 times longer, and at characteristic spatial scales 1,000 times larger. This is why the two systems appear so different in their observable properties, even though both are, at the most fundamental level, examples of the same phenomenon, a dormant black hole returning to activity after a period of inactivity. The physics is the same, the scales are vastly different. And that difference in scales is what makes the two systems complementary, rather than redundant as objects of study. By examining both the low mass, fast timescale regime, exemplified by Ansky, and the high mass, long timescale regime exemplified by J1007 plus 3540, and by finding the general patterns that span the full range of black hole masses, astronomers can test whether their theoretical models are truly universal or whether they are inadvertently calibrated to specific mass regimes. There is a further dimension to these awakening events that connects them to questions about the very origins of supermassive black holes themselves. In the current cosmological model, supermassive black holes formed very early in the history of the universe, within the first few 100 million years after the Big Bang, and grew to their present masses through a combination of accretion and mergers. But the precise pathways of that growth, the mechanisms by which black hole seeds of perhaps a few hundred to a few thousand solar masses grew to the million to billion solar mass monsters we observe today, are not well understood. One of the key puzzles is that growth through accretion cannot be arbitrarily rapid. There is a theoretical limit called the Eddington luminosity, above which the radiation pressure from the accreting material pushes back strongly enough to halt the inflow, limiting how fast a black hole can grow at any given time. This means that periods of rapid accretion must be interspersed with periods of lower activity, and the fraction of cosmic time a black hole spends actively accreting at or near the Eddington rate determines how quickly it can grow to its observed mass. Understanding the duty cycle, the fraction of time a black hole spends in an active state at a given accretion rate, is therefore directly relevant to understanding black hole mass assembly over cosmic time. Events like Ansky's activation give us a direct window into the triggering mechanisms that transition a black hole from dormant to active, and the rate at which such triggers occur in the local universe can be extrapolated, carefully and with many caveats, to constrain the duty cycles of supermassive black holes across cosmic history. There is also the question of what happens to the material in a galaxy's nuclear region as the black hole awakens. When Ansky's central engine switched on and began building its accretion disk, the radiation and outflows from that newly active nucleus began to interact with the surrounding gas and stellar population in the galactic center. X-ray photons from the hot inner disk irradiate the surrounding gas, ionizing it and altering its chemical balance. Outflows driven by radiation pressure or magnetic processes can push gas away from the nucleus, temporarily or permanently removing potential fuel from the black hole's vicinity. In more powerful AGN, these feedback effects can extend to the scale of the entire galaxy and beyond. But even in a relatively modest activation like Ansky's, the effects on the nuclear environment will be measurable over years of continued observation. Monitoring how the spectral properties of the gas around Ansky evolve as the activation continues, watching for signs of outflows, tracking how the luminosity changes in different wavelength bands over months and years, all of this provides a detailed portrait of the early-stage feedback from a newly activated nucleus. Another unprecedented observational opportunity, enabled by catching the system in its very first years of activity. As we look further into the observational landscape that these discoveries are opening up, it is impossible not to think about what the next generation of observatories will see. The Rubin Observatory in Chile, which began its 10-year legacy survey of space and time in 2025, will survey the entire visible sky repeatedly over the coming decade, detecting potentially billions of sources and flagging changes in brightness, with an unprecedented combination of depth and sky coverage. It will find new activating black holes like Ansky at a rate that could be tens or hundreds of times higher than previous surveys, building a statistical sample of these events large enough to address the rate questions and the diversity questions in a statistically rigorous way. The Athena X-ray Observatory, planned as the European Space Agency's next large-class X-ray mission for the 2030s, will combine a collecting area far larger than XMM-Newtons with high spectral resolution capabilities that will allow detailed mapping of the gas dynamics around active galactic nuclei. When Athena turns its gaze towards systems like Ansky, it will be able to characterize the accretion disk winds, outflows, and spectral features in a level of detail that current instruments cannot approach, and it will do this across a sample of sources large enough to begin answering statistical questions about how typical or atypical the behavior we see in Ansky really is. The James Webb Space Telescope, already transforming our understanding of the early universe, is contributing to this field in its own ways. Webb is particularly powerful for studying the infrared properties of active galactic nuclei, probing the emission from warm dust in the torus surrounding the accretion disk, characterizing the host galaxy properties, and studying AGN at high redshifts where their X-ray emission is shifted into wavelength bands less easily studied by existing X-ray telescopes. In the context of newly activating AGN, Webb's sensitivity to infrared emission from the nuclear region could reveal the presence of dust structures forming in the earlier stages of black hole activation, structures that absorb the optical and ultraviolet light from the accretion disk and re-emit it at infrared wavelengths, providing a complementary view to what XMM-Newton and NISA see in X-rays. And then there is LISA, whose connection to the QPE phenomenon we discussed earlier in this story. It is worth dwelling on this connection a little longer, because it is genuinely remarkable to appreciate how far-reaching the implications of Ansky's eruptions extend. The Laser Interferometer Space Antenna will open the millihertz gravitational wave window for the first time. In that window, the most numerous detectable sources are expected to be extreme mass ratio in spirals, compact objects spiraling toward massive black holes in galactic centers. LISA is expected to detect thousands of these systems during its planned 4-year mission lifetime, each one providing a precision measurement of the masses, spins, and orbital parameters of the black holes involved. These measurements will build a census of massive black holes in the mass range of 10,000 to 10 million solar masses, the regime that includes systems like Ansky's central black hole, a regime that is poorly constrained by current electromagnetic observations because black holes in this mass range are difficult to weigh precisely. but the EMRI signals will be much more than simple mass measurements. Because the orbiting compact object completes hundreds of thousands of orbits while its signal is in the LISA band, the accumulated gravitational wave phase encodes extraordinarily detailed information about the geometry of spacetime around the central black hole. In principle, LISA observations of a single EMRI can map the spacetime around a massive black hole with a precision that tests general relativity in the strong field regime to a level that no current observation can approach. The orbiting compact object is, in effect, a precise probe tracing out the geometry of curved spacetime in the extreme gravitational environment near the event horizon. The fact that at least some of these EMRI systems appear to also be producing observable QPEs means that LISA observations could be preceded, accompanied, and followed by X-ray monitoring campaigns that characterize the electromagnetic behavior of the same systems. This kind of coordinated multi-messenger observational program, gravitational waves from LISA simultaneously, with X-ray observations from Athena or its successors, represents the scientific frontier of the next 2 decades in black hole astrophysics. The awakening of Ansky and the discovery of its QPES is, in this context, not just an interesting discovery in its own right. It is a preview, a first glimpse of what multi-messenger science of massive black hole systems will look like when LISA begins operations. There is something philosophically profound about this that I find worth articulating, because I think it captures something important about the current moment in the history of astronomy. For most of the history of observational astronomy, we had one messenger, light. Photons arriving at our detectors from across the universe, carrying information about the objects and events that produced them. The development of radio astronomy in the mid-20th century, followed by X-ray, ultraviolet, infrared, and gamma-ray astronomy, as instruments moved to space above the atmosphere, expanded the range of that single messenger but did not fundamentally change its nature. We were always seeing photons, just at different wavelengths. The detection of gravitational waves by LIGO in 2015 changed this in a fundamental way. For the first time, we were receiving a message about the universe carried by something other than electromagnetic radiation. A message carried by the very fabric of spacetime itself, encoding information about objects and events in a completely independent physical channel. The joint detection of a binary neutron-star merger in both gravitational waves and gamma rays in 2017 demonstrated that multi-messenger astronomy was not just theoretically possible, but operationally real, that the two channels provide complementary and mutually reinforcing information about the same event. The QPE observations of Ansky and the EMRI connection they imply extend this multi-messenger vision to massive black holes and to the millihertz gravitational wave band. They suggest that the electromagnetic and gravitational wave universes are deeply intertwined in the physics of galactic nuclei, that the same accretion and orbital dynamics that produce visible radiation in X-ray telescopes also produce gravitational wave signals that future detectors will measure. This is a conceptual unification of two observational domains that were, until very recently, completely separate fields of physics. And as we step back even further and look at the full landscape of what we now know about awakening black holes, the picture that emerges is one of the universe as a profoundly dynamic and interconnected system in which nothing is truly static and nothing is truly isolated. The dormant black hole at the center of a quiet galaxy is not isolated from its environment. It is connected to the surrounding stars through the gravitational loss cone that determines the rate of stellar captures. It is connected to the larger galaxy through the gas flows that could reignite its accretion if conditions change. It is connected to the cluster environment through the heating and cooling processes that regulate the supply of cold gas. And it is connected to the gravitational wave universe through the EMRI systems that spiral toward it over millions of years, silent in light but speaking in space-time curvature. When that black hole wakes up, as Ansky's has woken up, and as J1007 plus 3540's has woken up, it broadcasts its reawakening across the electromagnetic spectrum. It shines in visible light as its accretion disk heats up. It erupts in X-rays as the inner disk reaches temperatures of tens of millions of degrees. It potentially launches jets that propagate for millions of light years through the surrounding cluster medium, bending and pushing against the hot gas, injecting energy that heats the cluster and suppresses star formation across scales 1,000 times larger than the galaxy itself. And through all of this, silently and invisibly, the gravitational wave background shifts subtly as the orbital parameters of EMR in the vicinity change in response to the new accretion disk that has formed. The fact that we are now, for the first time, catching these events as they happen, watching in real time as a black hole crosses the threshold from dormant to active, is not just scientifically important. It is, I think, genuinely wonderful. We are watching the universe change, not on geological timescales, not on astronomical timescales measured in billions of years, on timescales of years and decades, on timescales that fit within a human lifetime, on timescales short enough that the same telescopes that caught the first optical brightening of Ansky in 2019 will still be operating when researchers document the 100th year of its activity, if those instruments can be maintained. This brings me to something that I find both exciting and important to flag for anyone who wants to follow this story as it develops. The scientific literature on Ansky and related systems is growing rapidly. New papers appear on the ARXIV preprint server regularly, each one adding new data, new analysis, new theoretical interpretations. The NISA team, the XMM-Newton team, the SWIFT team, and the Zwicky Transient Facility team all continue to monitor the system. Each new eruption adds to the catalogue. Each evolution in the burst properties is documented and analysed. If you are someone who wants to go beyond the documentary summary and engage directly with the primary science, I encourage you to look up the original Nature Astronomy paper by Hernández-García and colleagues from April 2025, the follow-up NISA paper in Astronomy and Astrophysics from November 2025, and the monthly notices of the Royal Astronomical Society paper on J1007+3540 from January 2026. These papers are freely available through preprint servers and represent some of the most exciting primary scientific literature published in the past several years. Reading them directly, even if you do not follow every mathematical detail, gives you a very different experience from any secondary account, including this one, and forming your own view of what the evidence says, rather than relying on any narrator's interpretation, is always the more intellectually honest approach. I mean that genuinely and not just as a polite disclaimer. Let us now turn our attention to what researchers expect to see next from Ansky, and what the ongoing observations of J1007+3540 are likely to reveal as they continue. For Ansky, the most immediate scientific priority is continued high-cadence X-ray monitoring to track the ongoing evolution of the QPE properties. The doubling of the recurrence time and the quadrupling of the burst energy between 2024 and 2025, documented in the NISA follow-up paper, raises an obvious and pressing question. Will this trend continue? Will the eruptions become progressively longer, more energetic and less frequent as 2026 progresses into 2027 and beyond? Or will the evolution plateau, reaching some quasi-steady state in which the accretion disk and the orbiting compact object have settled into a stable configuration? Or will the eruptions eventually cease, either because the orbiting compact object finally crosses the innermost stable orbit and is swallowed by the black hole, or because some change in the disk geometry eliminates the disk-crossing behaviour altogether? Each of these outcomes would tell a different and important story about the physics. A continued monotonic evolution would support models in which a specific physical process, perhaps the gradual expansion of the outer disk radius as more material is delivered, is steadily changing the geometry of the disk-orbiter interaction. A plateau would suggest that the system has reached an equilibrium between the disk evolution and the orbital decay. A cessation would provide a direct measurement of the timescale on which EMR is spiral inward and complete their in-spiral in a newly formed accretion disk environment. There are also predictions from the EMRI models about the gravitational wave chirp, the gradual increase in gravitational wave frequency as the orbit decays, that are in principle observable through the QPE timing even before LISA launches. If the recurrence time is indeed tracking the orbital period of the EMRI, and if the orbital period is decreasing due to gravitational wave emission, then the recurrence time should show a systematic trend of gradual shortening over years of observation, interrupted or modified by changes in the disk geometry. Precisely measuring this trend requires years of monitoring with the sensitivity and cadence that NISA and XMM-Newton provide, and represents one of the most exciting long-term observational projects currently underway in X-ray astronomy. For J1007+3540, the ongoing and future science is centered on understanding the interaction between the reborn jets and the cluster environment in ever-increasing detail. The current radio images from LOFAR and UGMRT provide an extraordinary snapshot of the system, but they are a single moment in the evolution of something that is changing on timescales of thousands to millions of years. Future radio observations with upgraded instruments and with new facilities like the Square Kilometre Array currently under construction in South Africa and Australia will provide higher resolution, higher sensitivity images that can map the detailed structure of the jets, measure the spectral properties of different regions of the plasma, and track any changes in the morphology over years of repeated observation. The Square Kilometre Array, when fully operational in the coming years, will be the most sensitive radio telescope in history by a considerable margin. Its ability to detect faint extended radio emission from ancient plasma lobes will revolutionize the study of episodic AGN activity, finding examples of multiple generation radio galaxies that current instruments cannot detect because the faded plasma from previous eruptions has become too faint. The statistics of multiple generation AGN, how common are double or triple generations of activity, how long are the typical dormancy periods, how do the jet properties change between episodes, all of these questions will become tractable with Square Kilometre Array data in a way they simply are not with current instruments. There is also the question of what the intracluster medium observations at X-ray wavelengths from observatories like Chandra and XMM-Newton can tell us about how J1007 plus 354O's reborn jets are currently heating the cluster gas. In other well-studied radio galaxies and clusters, X-ray observations reveal cavities in the hot gas, regions where the jet plasma has pushed the gas aside, surrounded by bright rims of compressed heated material. These cavities are direct calorimeters. By measuring their size and the pressure of the surrounding gas, astronomers can estimate how much energy the jets have injected into the cluster medium, providing a direct measurement of the AGN feedback power. For J1007 plus 3540, detailed X-ray observations of the cluster gas around the reborn jets would provide exactly this kind of energy measurement, connecting the radiomorphology to the thermal structure of the cluster in a way that tests models of jet-cluster interaction directly. The broader picture that these two awakening black holes are painting together is one in which the boundary between cosmology and astrophysics, between the large-scale structure of the universe and the intimate physics of individual galaxies, is revealed as deeply blurred. What happens in the nucleus of J1007 plus 3540, in the orbit of a compact object around Ansky's central black hole, in the assembly of a new accretion disk from gas that has been slowly drifting toward a galactic center, all of this has consequences that propagate outward through the surrounding environment and connect to the larger scale patterns of structure and evolution in the cosmos. A galaxy cluster whose central AGN reactivates after 100 million years of dormancy experiences a change in its thermal energy budget that affects how cold gas can accumulate, which affects how many new stars form in the cluster's central galaxy, which affects the stellar populations and metallicity of that galaxy for billions of years into the future. A newly activated QPE system like Ansky, if its EMRI interpretation is correct, is generating gravitational waves that are, at this moment, propagating outward through the cosmos at the speed of light, carrying information about the orbital mechanics of a system 300 million light-years away that future detectors will measure. The universe is not compartmentalized, every event echoes, and perhaps the most profound echo of all is the one that resonates back toward us, toward the people doing the watching. We live in a galaxy with a dormant central black hole. Sagittarius A star is quiet right now, producing modest flickers of activity but nothing that would classify it as an active galactic nucleus by any standard definition. But it was not always so quiet. There is evidence in the gamma-ray sky of large structures called Fermi bubbles, extending tens of thousands of light-years above and below the plane of the Milky Way, that appear to be relics of a more powerful episode of activity by Sagittarius A star in the relatively recent past, perhaps a few million years ago. The echoes of that past activity are still propagating through our own galaxy today, and Sagittarius A star could become active again. Not necessarily dramatically, not necessarily with the violence of a quasar or even a modest AGN, but the reservoir of gas in the inner region of our galaxy, the complex interplay of stellar winds, supernova remnants, and gas flows in the central molecular zone, is a potential source of fuel that could, under the right circumstances, deliver more material to the central black hole and trigger a new episode of accretion. The timescale for such an event is uncertain, and the probability within any particular human lifetime is low. But in cosmic terms, The return of activity to Sagittarius A star is not unthinkable. It is just a matter of when conditions change. In the meantime, the awakening black holes we observe at safe distances of hundreds of millions of light-years away are our laboratories. Ansky, erupting in X-rays every 4 to 10 days in the heart of a galaxy in Virgo, is showing us what the early stages of black hole activation look like in exquisite detail. J1007 plus 3540, blasting its cosmic volcano across nearly 1 million light-years of space in a distant cluster, is showing us what the reactivation of a long-dormant giant looks like at a scale that reshapes its entire galactic environment. And the theoretical frameworks, the EMRI models, the accretion disk instability models, the AGN feedback models, the gravitational wave predictions for LISA, are all being stress-tested against these new observations in real time. This is science as it actually operates, messy, uncertain, contested, and thrilling. Not a clean march toward preordained conclusions, but a genuine encounter with phenomena that surprise, that challenge our models, that open questions we did not know we had, and that promise, with more data and better theory, to resolve into understanding. We are living through an extraordinary moment in the history of humanity's attempt to understand the universe. The instruments we have built, the surveys we have committed to running for years and decades, the space missions we have launched and maintained and will continue to build, are giving us eyes and ears that none of our ancestors possessed. And with those eyes and ears, we are watching the universe breathe. We are watching its most massive objects wake up, not as metaphor, but as measurable physical reality. We are watching light leave a distant galaxy 300 million years ago, travel across the entirety of recorded human history and vastly more, and arrive at our detectors in space to tell us that something extraordinary happened there, is happening there still, and will continue happening for years and decades as we watch. The black hole in SDSS 1335 plus 0728 is still erupting. As of the latest published observations, Ansky continues to generate its extraordinary quasi-periodic bursts of X-ray radiation, each one more energetic than the last series, the recurrence times continuing to evolve in ways that theorists are actively working to explain. The reborn jets of J1007 plus 3540 are still pushing outward through the dense intracluster medium, bent and compressed and sculpted by the cluster environment, carving their way through a medium that will in turn be changed by their passage. The observing campaigns continue, the data accumulates, the models evolve, and somewhere in the archive of the Zwicky Transient Facility, in the long baseline monitoring programs of Swift and XMM-Newton, in the timing data of NISA, and in the new surveys just beginning their decades-long stares at the sky, there are almost certainly other black holes in various stages of their own awakenings, waiting to be recognized for what they are. The universe is stirring. And we are, for the first time, awake enough to notice. Thank you for spending this time with Deep Space Intelligence. If this story has sparked questions, if you want to dig deeper into the science we have discussed, I encourage you to seek out the primary literature and form your own views about what the evidence means. The papers are there, the data is there, and the questions are genuinely open. That is what makes this the most exciting time in the history of black hole astronomy. My name is Liam, this has been Deep Space Intelligence, and we will see you on the next one.